Right, so I'm going to cover an important area in terms of privacy, and that's to do with zero-knowledge proofs. So what are zero-knowledge proofs? ZKP, zero-knowledge proofs. Well, zero-knowledge proofs are all about proving something. So we might have Peggy, the prover, proving something to Victor, the verifier. In this way, Peggy proves something to Victor without Victor actually seeing what the original data was. So with ZKP, we make sure that Peggy doesn't reveal any sensitive secrets. So the core of this is the concept of privacy-preserving knowledge exchange. And in the classic case, what we have is Alibaba's cave. We might draw it like this, and we have a secret passway. And in the Alibaba's cave, we of course have Victor and we have Peggy. So within this scenario, what happens is that Peggy goes into the cave into one of the entrance points, A or B. Victor doesn't see Peggy going in, but Peggy goes in, and then Victor calls out that Peggy should reveal herself through exit A. And in this case, Peggy will do that. And each time, Victor will ask Peggy to appear out one of the entrances, and depending on which one Peggy chooses, she will get it right if she knows the password all of the time, but eventually she will get it wrong if she does not know the password. So for example, if Peggy went through A and Victor asked for B, then Peggy could not appear out of B. In this case, it's really 1 over 2 to the power of n is the probability that 1 minus this is the probability that Peggy knows the secret password here. So every single time that we do it, we increase the chances of Victor knowing that Peggy does know the password. And Peggy does not reveal the password at all when she's doing this. So this is really at the basis of our zero-knowledge proofs. Some way that we can actually prove that something is true, or that we know some data without actually revealing it. One of the first papers which actually defined a method to be able to implement a zero-knowledge proof method was the Viet-Shamir method. With this, Peggy has a secret value. Let's call that secret value y. Then Peggy will take g to the power of y and mod of a prime number, and we'll call that big Y here. So in this case, Peggy will register with Victor. So we have Victor here, and we have Peggy over here. This is the secret that Peggy wants to preserve, and this is the value that Victor knows Peggy, but will not reveal the value of Y because we cannot solve this for the value of Y in this case. So now we will generate a challenge. So Victor sends over a value of C in this case, and Peggy will generate a new random value. And let's say that value is X. Next, Peggy will generate a value E, which is the value of X minus the secret times the challenge. And we'll also take that in terms of mod P, but we'll just leave that off just now. So the calculation is the new random value, the Y value that Peggy has a secret, and the challenge value that Victor has sent. Now, Peggy must solve the puzzle and to provide the right answer. So Peggy sends back the value of E that she has computed, and will also send back the value of X, which is G to the power of X mod P. So the value of X will go back there, and then this will hopefully be the proof that Peggy knows the value of Y. So over here, what we do is that we take G to the power of the value that came back to the power of E here, and then we'll take the secret, the value that Victor knows, Y, and we'll raise it to the power of C. Okay, so it's G to the power of E and Y to the power of C. We also do a mod P again, as always, and it should work out. Okay, so let's see if that works. So that's G to the power of E, and this will be G to the power of Y to the power of C, which is that mod P. Now we have G to the power of X minus YC, G to the power of YC mod P, and we end up with G to the power of X mod P. And that should be the same as this value here. So Victor will take these values and then take the E value, compute, and then check against the value that Peggy actually sent. And if they're the same, then everything is good. We can enhance this even more if we now take the hash value of X and C. Okay, so we take the challenge, we take the X value that we computed, we concatenate them together with their bytes, and we take a hash, say a hash 256 of that. And then over here, what we need to do is do the same again, but this time we'll take the hash of that value, and we'll compare the two hash values together, and if they're the same, then Peggy has proven that she still knows the value of Y in this case. So this is the Fiat-Shamir method, and it's still relevant today. And what we can do, because discrete logs can be quite challenging if the prime number is quite large, we can convert this easily into an elliptic curve method. So for the elliptic curve method, what we have is that we send over the value of YG, where G is the base point and Y is a scalar value, the secret. So over here, we register the value of YC just like we did over here. Then we send the challenge, that's just the same, and we calculate our E value as we did before. E is equal to minus YC. This time we do a mod of n, and where n is the order of the curve. We work out x, and x becomes xg as a point. Then we take the hash of the point concatenated with c, and we can send that over. On the other side, we take the hash of EG, and then we take C. We do an add rather than a multiply for elliptic curve. So we add on the point C, Y. That becomes the hash of x plus yc, x minus yc, g plus c, and y is that. And then eventually these, because this is a negative, these two terms cancel, and we end up with the hash of x g concatenated with the message with C. Okay, so in this way we can convert the Fiat-Shamir method, where we take discrete logs and we convert them into this form here, where g is the base point and x is the scalar value. When we have an operation such as this, that is equivalent to an adding operation when we have our elliptic curve points. Okay, so exponential becomes multiply, and multiply becomes add in elliptic curve, and discrete logs here. Okay, so that's how we can use the Fiat-Shamir method to be able to do this. Then what we can do is that rather than generating the challenge, we can generate our own hash value, and this becomes a non-interactive challenge. This becomes a non-interactive zero knowledge proof. In this case, we generate an x value and the challenge for it, and we can send back the results to be able to compute these values. So next, let's look at another advancement, and this advancement was the Schnorr ID scheme, and it was based on the Fiat-Shamir scheme. And we'll outline it in discrete logs, but it's easily converted into elliptic curve methods as we have here. So in this case, what we have is that we have a secret key, and we'll call that secret key X, and we have a public key big X. So what we're going to do is prove the identity of someone using zero knowledge proofs. And with these X, the X secret value, the private key, and X the public key. So initially what we do is, as we've done before, we'll take a value, in this case we'll call it Y here. We send Y over, and in discrete logs it's g to the power of Y mod P becomes the value of Y here. Then what we do is that we generate our challenge here from there, and we compute a value Z is equal to Y plus XC. Okay, and what we'll do is we'll take our private key here, and this is going to prove our private key using zero knowledge proofs and this secret. Now I would take that mod P again, and now what we do is that we send over our values here, and we need to prove that y times x to the power of c will equal g to the power of z. So in this case, the public key is known by the capital X. So x is equal to g to the power of x mod p. And this is the public key of Peggy. And this is the private key. So Victor knows the value of x, raises it to the power of c, and then multiplies that by the value of y that have, and then the value of gz is also sent over. So g to the power of z is sent over as this value here, and we can prove that this value is equal to this value. And we do that by saying the y is g to the power of y, x is g to the power of x to the power of c, which is that, and then we end up with g to the power of y plus xc, which should be the same as this here. In this way, we prove the private key matched to the public key. So we prove the identity of Peggy through her public key and the registered secret, so that she still knows her private key here. And this is the public key that she's known by. Again, we can easily convert this into elliptic curve methods if we require. And from there, we can easily just convert the hash value. So we could take the hash of z and the hash of the message together to produce this zero knowledge proof, and then over here we would just take this value and add it on to the c value, and we would end up with the same hashed value on either side. So that's the Schnorr ID method, and it can be used for a wide range of applications. One of the applications it's been used for at the present time is with a post-quantum crypto method for digital signing. And with this, one method is known as dilithium, and it produces a digital signature using lattice methods. But at its core is this and this method here. And what we do is that rather than having the challenge, we generate the message. And the message becomes part of this z plus x, remember the private key, plus m. We have the message and we don't have the challenge anymore, but then we can, obviously in discrete logs, we can have g to the power of z becomes z. We can take the hash of z and the message, and that becomes our zero knowledge proof. On the other side, we just do the same, but in this case we take the hash of this concatenated with the message, and if the two tie up, then we have proven the digital signature of Peggy for her private key X here. and this is our public key there. So the public key is proving the signature on the message. So what we pass over is the message, of course, and this value here. And we have our message in there too, to be able to check. So we can see that we can use the Fiat-Shamir method in terms of even digital signing. The zero knowledge proof, the identity checking, and now into a post-quantum digital signing method. Okay, so another area where we can apply zero knowledge proof is to prove that we know the answer to a problem without actually giving the answer away. So a problem might be a quadratic equation, such as this. So the answer to this is this. Where x is equal to 7 or x is equal to -6 would solve this equation. Okay, because we have 49 minus 7 minus 42 is equal to 0. So let's say that we had to prove to someone that we knew the answer to this equation without actually revealing the answer. So what we do is that we use a method called crypto pairing. And crypto pairing has a very special set of relationships. What we have is we have two elliptic curves, and then we have a pairing between them. And with this we have some special operations. This defines the mapping of one point on one curve to another one, G1 and G2, say. Then, if we have a point U on this curve, and we multiply it by A, and we have a point V on this curve, and we define that as a pairing. When we operate on them together, we get a result of the pairing, so A and B. With pairing, then, we actually also have U and A, B. So this is equivalent to moving the A over there to become AB. That will give us the same answer when we pair our points together. And it's also the same as U and V to the power of AB. We can take the A and the B out, and we can take the pairing point, pairing value, and raise it to the power of AB. And even we can say BU and AV. So these are the special conditions that we have for our crypto pairing. So let's see if we can prove, Peggy can prove to Victor that she knows the answers here. So with this, we have another method for pairing. And what we have is 2 points, two of the same points, to any value k is always equal to 1. So we take a point here and a point there, we pair them, it doesn't matter what we raise them into any power, we will always get a value of 1. So now if we try that with inside our little zero knowledge proof, we can take our equation and do that. That should equal 1. Now we'll take that and we can split that up now so that that becomes that, and then we end up with that, and that is equal to 1. From here we can then move the x's in, and that becomes xg and xg. That becomes xg and minus g, and then that becomes g and minus 42. G is equal to 1. Now all Peggy has now to do is to show the value of xg, because Victor can now take the value there and do this pairing, do that pairing, and do that pairing, and if the value ends up at 1, then Peggy has proven to Victor that she knows the value of x. So she takes a base point on one of the curves and then multiplies it by the value of x that she finds, and she will pass that to Victor. Victor then computes this pairing to the same values, does this pairing with the value that's been sent here and a value of minus g, and then does this pairing which is g, and the minus 42 is a constant. If Victor finds that that is equal to 1, then Peggy has proven that she knows the value of x here. Okay, so that's been a brief introduction to the wonderful world of zero knowledge proofs. These methods are used now in ZK snarks, but we're still fundamentally also using these methods here, and we can see we're now using zero knowledge proofs in terms of lattice methods. So rather than using discrete logs or elliptic curve methods, we use polynomials here for these values. Okay, so that's been a brief introduction to zero knowledge proofs.